So in this video, we are moving on from consumer products, so that was the alcohol homologous series and the carboxylic acids, and we're going to talk about the last part of Unit 2, which is energy from fuels. So from this topic, we're really going to look at two main components. We're going to talk about something called combustion equations, and then we're going to explore how we measure the energy produced when we burn fuels of certain types. So before we do that, we first want to think back about what a fuel is from National 4, because the main focus of this particular video is going to be the combustion equations component. So when we think of fuels, we need to think of a substance that burns to release energy. And by that, we're talking about a chemical reaction in which the fuel reacts with oxygen to make a new substance, or new substances, plural. So we want to think about something releasing energy, reacting with oxygen, and forming something new. And the word for that particular type of reaction, because we are burning it in oxygen, is called combustion. So a combustion reaction is burning something in a plentiful supply of oxygen, which is complete combustion, or an insufficient amount of oxygen, which would be incomplete combustion. But for just now, as long as we recognise that combustion is burning a fuel in oxygen, that is fine. And of course, if we're releasing energy, this is an exothermic process. Energy is released in the form of heat energy to the surroundings. So, both hydrocarbons, which we should be familiar with from the last topic, and alcohols from consumer products will readily combust. That means they're quite easily burned and they will release a lot of energy. And so the following combustion equations can be written. So when you think about combustion equations, I want you to remember that when you burn a hydrocarbon and oxygen, you get carbon dioxide and water. Those are the two new substances that are formed. And when you burn an alcohol and oxygen, you get carbon dioxide and water. It is the same. So we're going to explore in this video why that is, or how that could be. So for example, you could have methane, which is one of the simplest hydrocarbons. That is the first member of the alkane homologous series. And you could burn that in oxygen and get carbon dioxide and water. Or you could burn butane in oxygen and get carbon dioxide and water. Or you could burn butanol, which is an alcohol, in oxygen and get carbon dioxide and water. So you see the theme here. No matter what I'm burning, whether it be a hydrocarbon, doesn't matter the chain length, or an alcohol, I get not just the same family of chemicals, but I get the exact same chemicals. So how can that be? How can they be all the same regardless of what we burn? And the answer to that question is using balanced equations. So a key part of this topic at National 5 is not just recognising what chemicals we're using and their properties and how to write their formula and so on, but manipulating balanced equations, often to find some kind of value or find something out, or maybe just balance the equation itself, or come up with a balanced equation yourself. So particularly for this topic, particularly for combustion equations, the balancing of those equations is a skill that you want to be quite good at. Unfortunately, because it's the same product all the time, it's quite an easy balancing system to go through. So what we're going to do is take each of those three examples and balance those equations using the chemical equations for those reactions, and it'll be dead easy. So if we take the first one, we think about burning methane and oxygen and getting carbon dioxide and water as our products, as our new substances. This is what that is going to look like in chemical equation form. So we have CH4, so a carbon with 4 hydrogens bonded on, oxygen, our diatomic gas, diatomic meaning 2 atoms, so we've got O2, and these will react together to form carbon dioxide, CO2, and water, H2O. Now, before we start balancing, and I'm going to change to a different colour to emphasise this, when we're balancing equations, we cannot change these little numbers. We can't change the subscript numbers of the chemical formula. Now, the reason we can't do that is because if we change those numbers, we are changing what the chemicals are. We are not allowed to do that. We can't change what chemicals we're working with. We can change how much of the chemicals we have, i.e. how many moles of each chemical we have, And that's exactly what we're going to do with the big numbers in red, but we can't change what the chemicals are. So never change the little numbers is the rule here. But if we want to balance this, what that means is we're talking about a conversion of mass, okay, a conservation of mass, sorry. So basically in any chemical reaction, every atom of every reactant, in this case methane and oxygen, will appear on both sides of the chemical reaction. So if there's carbon on the left, there will be carbon on the right. If there's oxygen on the left, there will be oxygen on the right, so on. No atom disappears, and no atom appears from nowhere. They just change what they're bonded to. Now, what does that mean? That means the overall mass that we start with, i.e. the number of each atom that we have, so 1 carbon, 4 hydrogens, 2 oxygens, etc., must be the same on both sides of the chemical equation. And that is called the law of conservation of mass. So we can't make stuff out of thin air, and we can't make stuff disappear. So whatever we have on the left, we have to have on the right. And it doesn't necessarily have to be what we start with. We can change the numbers on both sides, as long as at the end, it's a nice balanced equation. And that's why it's called a balanced equation, because it has to be level on both sides. So if we look at this equation, some of our elements, some of our atom types are balanced, some aren't. So we have 1 carbon on the left-hand side, because there's 1 here, there's none here, so there's just the 1 from the methane. And on the right-hand side, if we look at both of our compounds, we have 1 carbon. So the carbons are already balanced, so we don't have to do anything to them just now. The hydrogens are next. We have 4 hydrogens here, that's what the little 4 is telling me. And on the right-hand side, there's none here, and I've got 2 here. Now, 4 here, 2 here, that is not balanced. And remember, we can't change this little number to a 4, because that would be H4O, and that's not a thing. That's not water, we can't do that. The only thing we can do is add a big number at the front of the entire chemical. So we need 4 here, we only have 2. The only sensible choice we have to get this to 4 is to multiply the whole thing by 2. Now, in doing that, not only do I now have 4 hydrogens, which is what I want, because there's 4 on this side, so they're now balanced, I now also have 2 oxygens, because that big 2 affects the entire compound. So, I've now got in total on the right hand side, 1, 2, 3, 4 oxygens. Not my original 3 that I started with. And so if we go back to the left, and we see how many oxygens we have on the left, we only have 2. Now this is an easy fix, because we can just do what we did to the water on the right hand side. If we multiply that by a 2, we now have 4 oxygens on the left and on the right. 2 from here, 2 from our newly balanced water, 4 from our oxygen. So if we now go through all the chemicals, all the elements, we've got 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side. So this is now a balanced chemical equation, because the overall mass and the number of each atom is the same on both sides of the equation. And that's all we're going to do to the following 2 examples. So if we now look at butane plus oxygen, our argument is it will give us, or should give us, the exact same chemicals. Now how can that be? Well, it can be because all that happens is we end up with a different number of moles of those chemicals. We get more or less of these chemicals being produced. And that is how this works. So this time, if we have a look at our molecular formula, we have C4H10, following our general formula for butane, for the alkane family. Oxygen is the same, carbon dioxide is the same, water is the same. Okay, these will never change. It's just the thing that we're burning that will change. And that makes our life a little bit easier, because we go through the same process each time. First of all, we try to balance the number of carbons. Then we balance the number of hydrogens. And then we work back to balance the number of oxygens with this. That's the easiest way to do it. And that makes sure that everything stays nice and tidy, and we don't have to go back, scrub things out, make any mistakes if we're doing it properly. So we have 4 carbons on the left, we only have 1 on the right. So they're not balanced this time. So this time we're actually going to have to put a big number in front of our carbon dioxide 2. So we need 4. Let's turn that into a 4. So that sorts our carbons out. Let's put little ticks above them to keep it right. However, just like the water above, we now have 4 times 2 oxygens. This was originally CO2, we've now got 4 of them, which means it's 4 times 2. So that's 8 oxygens here and 1 here. We've only got 2 over here. That's going to be an issue. But we're not going to deal with them just yet. We're going to look at our hydrogens next. So 10 over here on the left, only 2 on the right in our water. So again, we're going to have to multiply that entire thing by something that will give us 10. We already have 2. Let's select a 5. 5 times 2 is 10. 10 on the left. The hydrogens are now balanced. Go back to the oxygen. Okay, so now we have 4 times 2 oxygens from the carbon dioxide, which is 8. And then a 5 from the water. So we've got 8 plus 5 oxygens. So that's 13. Now 13 might seem a bit scary at first because it's an odd number. And we've got a 2 here. Now don't let that put you off, because all we have to do, if there's a 2, is think, okay, there's going to be a half involved here. And you can either represent that as a decimal or as a fraction. I find it easier to do a fraction because all you have to do is take the number that you have here, take the number that we have over here, and then think, okay, well, if I put that number next to my oxygen and times it by 2, I have double what I need. So all we have to do is half it. So the correct answer is 13 over 2, or 6.5. You can write 6.5 if you like, because that is what we need to multiply by 2 to get to 13. But if that is a bit complicated, just think, okay, take the number of oxygens I have over here, put it on there, realise that I've got double the number that I need, divide it by 2. So we've ended up with 1 mole of butane plus 13.5 moles of oxygen give me 4 moles of carbon dioxide and 5 moles of water. That is now a balanced equation, because again, we have the same number of atoms on the left as we have on the right. So to finish off, let's do that last example, and that was reacting a different homologous series, burning a different homologous series. So we now have an alcohol, and we want to react that with oxygen, again to produce carbon dioxide and water. Now, we have a different functional group. This time we have an OH involved, but we're going to go through the exact same process. We're going to balance our carbons, we're going to balance our hydrogens, and then see where we are with our oxygens, and see if it's just as easy. So we have 4 carbons, 9 hydrogens, and an O and an H in our butanol. And of course, everything else is the same. So again, starting with our carbons, 4 here, 1 here. What are we going to do? We're going to multiply the right-hand side by 4. Now our carbons are balanced. Let's move on to the hydrogens. Now, here is a case where we have more than one instance of hydrogen. We've got 1 here, 1 here, or 9 here and 1 here. Bundle them all together, include them all as a total. We always want to think in balancing equations about totals for the left-hand side and totals for the right-hand side. So we have 10 on the left, 9 plus 1, and we have 2 on the right. This is very similar to our example above. So we want 10, we only have 2, let's multiply it by 5. Okay, now what effect does that have on our oxygen? Well, that means just as before, in the previous example, we've ended up with the same numbers. So we know again, we have 13 oxygens. Okay. On the left-hand side, it's slightly different this time, because we don't have to multiply this 2 by 13 over 2, because we've also got an oxygen here. So we need 1 less in our oxygen part of the equation, because we've got an oxygen atom in our butanol. So we've actually got 3 over here just now. So if we take this one away from the total that we need, because we've already got 1, we realise that we need 12 oxygens to get a balanced equation. Because if we have 12 here, we'll have 13 in total, adding on this 1 from the butanol. So in order to get 12, this is actually a bit easier than the previous example, because we have 2, we need to get to 12. What do I have to do? Multiply by 6. So last time it was 6.5, this time it's only 6 because we've got an extra oxygen over here. So we've got 6 times 2, which is 12, plus 1, which is 13, 13 oxygens on the left, 13 on the right. So always go through that process for balancing combustion equations. Try and balance your carbon atoms first, then deal with the hydrogens, and then by that point you should have included numbers on both of your new products, leaving only the oxygen left to balance.